Okay. So guys, today we are starting with the chapter 2. I think I gave you a good introduction last time about the entire, um, how radiation affects the solid. And finally, we were looking at some TEM images. And then there was a group of TEM photos were there where I was talking about different phenomena from where you saw the black dots, then you saw the dislocation loops or lines. And then we talked about voids that are created. Now, in today's class, what is happening is we will talk about, we will talk about fundamentals of radiation damage. Because this is effects of radiation on solids, this class, and how does a radiation interacts with solid, and then your defects are created. So radiation interacts with solid, defects are created. This is how the entire sequence of events are. And today we will talk about the fundamentals of radiation damage and defect production. And I just want to ask one thing. Do you guys know about SRIM? SRIM is a software. How many of you know about it? SRIM, TRIM, have you heard about it or not?
I'm familiar with it. I've used it a lot.
Oh, you have used it a lot. That's a very good thing. And other people?
I used it in materials.
Okay, very good. So you guys know. So Olamide, you?
I've not used it before.
Okay, very good. So
I've not used it. I've not.
you have not. Okay.
No.
Your two other classmates have used it. So that puts you at a good spot. So what the homework today is about that you have to, the first homework that I'm giving you is using SRIM. And because it's a software kind of a thing, so I did not know how many of you know or how many of you don't. So I gave, instead of 2 weeks, 3 weeks, because it's a software. And I can give you the link of the homework, and we can talk about that. Or yeah, and in that you have to do certain SRIM calculation. And you have to, I have given you initial ion, and then I have given you the final material on which the initial ion is making collisions with, and then you have to determine the range and everything. So I think Nari, you can help Olamide on that.
Yeah, if he needs any help. I can also send him Dr. Graham's slides back in the day when he taught us how to use it.
Okay, that is very good, because this is a little advanced thing, so I assume that I can give you a tutorial, but it's a very something very easy. Okay, so if you need a tutorial, you can let me know, and I can, but I believe you should be able to do it. So today we are doing something, the same thing. We are doing interaction between energetic particle and solid. And this is what will be our main thing. So let us understand what it is. So guys, here we know that a solid, it consists of stationary atoms, right? And we have a massive, we all know this thing. What is a solid about? It has a nucleus, it has a electrons. So this is a solid which has a nucleus and it has electrons around it, right? And like this, you have the entire solid. You have a nucleus and electrons. So if you have a system like this, where you have a nucleus and an electron, and I make a lot of things like this is kind of solid, and your solid could be any material. It could be either gold, aluminum, any material in the periodic table, you can represent it like this. So this is your nucleus, and this is your electron. Now, this is your what we call the solid. Now, on this solid, what we are doing is we are studying here today radiation effects in solid. So we are bringing some kind of energetic particle into the solid. So this energetic particle could be any particle, which could be, this can also be any element from the periodic table. This can also be any element for the periodic table. Now, when it comes in, what do you think the interaction will be? Interaction will be one with the nucleus, and other interaction will be with the electron. So these are the two kind of interactions we will study. So this is generally what it is. It's a kind of already an atom that comes, from your accelerator. It's an energetic atom. Generally, it doesn't have its own electron. It is stripped. So it would be, something like, you can say if it's a helium, He3 plus, or something, something, or you can have, I would say, fluorine. I'm just going in the beginning, any energetic ion, and that will have its own state. That means it doesn't have outside electrons. It goes in, it makes a collision with neutron and electron. So because now it doesn't have its own electron, it is stripped of its own electron. So it just goes and make a collision. So this is an atom. So now if I strip the electrons of this is a nucleus. So now when the nucleus makes a collision, it's a ballistic collision. And idea is this thing comes with the energy between, say keV to meV. That will be the energy that you will be using generally for, your simulations. So this energy, when it goes here, it is very high energetic. But after some time, this ion will stop in the material. Why it will stop? Because it will, can anyone contribute here why it will stop? Because it will lose energy when an energetic atom enters the solid. It will lose energy due to interaction with neutron and electron. So it will stop eventually because it will make collisions with them and it will lose energy. And you will find that where does it stop? So for example, if I make, more of a D zoom, if this is my material, which is like a 3D material, right? And I have an atom that goes in, an energetic, you can say ion energetic atom that goes in, and this is a 3D, you will see that in the beginning, it will transfer, it will go inside this material like this. Afterwards, it will make this kind of shape and it will stop. What is this kind of shape? This kind of shape is that material. So this is the final point where, it stopped. So it could stop like 6 micrometer in the material. It could stop like 3 micrometer in the material, and it could stop. And this is known as range, right? The how much this energetic ion, it came into the material and stopped. That is known as range. Now, this was your incident ion. How did it stop? Because in between, it had all these, here, it had all these atoms when it was going in, and there it, and now if I zoom in, it is making collision with neutron and electron, and it was an atom here, right? And it is making, so overall it is making two kind of collision. One is the ballistic collision that it is making with the neutron, and other, it is making collision with the electron. And that is known as electronic energy loss. And that the one that it is making with the nucleus, it is known as nuclear energy loss. So this is very important. Now, that is the idea today, and you will do this homework. You will go on this something called SRIM or TRIM, and you can find it online, and you can ask me if next class, because I assume you are advanced class, so you might have done it before. We will do this calculation where we will artificially, bombard an initial atom, we'll put it on a solid, and we'll calculate these range. So in this simulation, you can select everything. You can select what is the incident particle, what is the bombarding solid on which it is getting bombarded, what is the energy of this ion, and where does it stop, what kind of nuclear energy loss it has made, and what kind of electronic energy loss it has made. So this is the entire setup that you will do in SRIM, right? So that is the idea that today we'll understand the physics behind it. But eventually, after understanding the physics behind it, we'll go to that online software that you can download and you can create things. So if you want, I can share my screen. Just let me Google it. Give me a minute and I can share my screen. Where to download? Give me a second. So guys, here it is. So let us see. I'm just trying to escape. Give me a second. Okay. Let me just share my screen. Okay. Give me a second, I can just share. So if I go here to the people who don't know, you have to go here. This is SRIM. And so this is the software, interaction of ions with matter. Today we are doing theory of it. Your homework is that I will give you after the class, I'll send you. It is to calculate a lot of, your, how to say, nuclear stopping power, electron energy stopping power, ranges of ion, and stuff like that. So what it is, let me try to give you a good one here. I went yesterday as well because I don't have it in my Mac. That's why. Okay. Just a second, software. Okay, this is the software. And when you do it, I was on the right place yesterday. Give me a second to. And when you go there, review, you have to buy this, but you don't have to buy anything. Mhm. Okay, you can install it. And it is 2013, because after that people, they did not really put efforts on it. These guys, Ziegler and everyone, maybe he got, really, really, yeah, here it is. Because he was old by the time he gave this, because this has been in it. So this is what I'm talking about. So you can create this. I do not have Mac, but I can, show you if somebody doesn't understand. So what is happening here is, this is the kind of plot that, where you go inside the material. So right now, this is going inside the material here. I can annotate. Okay, so this is going inside the material. Right. It will not do it. Yeah, it will do it here. What's happening? Yeah. So this one, you see here, this is how it looks. This one here. And I want you to plot this. So what is happening here is, there is an incident ion, and this incident ion, it goes inside it. And when it goes inside it, then you see it, slowly, what is happening is, I'm increasing the number of ions, and the collisions are increasing. And this is making two types of collisions. So this was a tungsten right now. And here we have a hybrid, but you don't have to do hybrid, you can. But now we have a tungsten here, some kind of incident ion is coming. And that incident ion, as you see, the collisions are happening. And after that, it will stop at a particular depth, right? So what are the two types of collisions happening here? Two types of collisions are happening is, one is the inside one is interacting with the nucleus, and the other it is interacting with the surrounding electrons, that is around the nucleus. And you can calculate both. So you can create this, and you can let me know, because it's a very, very easy software. Once you download it, it will start, from the beginning, that you can choose an ion. It goes on the material. After that, it can create these ranges and things like that. So let me know if you don't understand, but idea is that today's class, we will go a little bit in theory about it, how the things are happening. Okay, with that, I'll go back to the class. Okay, so ultimately, this is the idea. Guys, do you have any questions? It looks easy. It is easy. So solid, it goes, so in solid, how does it interact with the incoming radiation? It either interacts with nucleus or the electrons. Now, there are three types of energetic particles are there. One are the neutral particles. So guys, there's a lot of things involved. Now, when this is a solid like this, the incoming particle could be of many types. One, it could be neutral. Neutral would mean that it doesn't have any charge. Neutron and gamma ray are the neutral particle. Other particle are the charged elementary particle. So what are the charged elementary particles? Charged elementary particles, they would be either proton, positive, alpha particle, electron, they will be all charged. So you can choose not only your entire periodic table, remember, and can start putting them inside you can take them to any accelerator lab. They will have a diode, here helium, lithium, but you can also choose these neutral elementary particle or charged elementary particle. We know that alpha, beta, gamma is one of them. And then you also have neutrons, right? So this is how, if you remember, we can also put them. But exactly, it's a neutron here that is there. Now it's an electron, which will be, beta particle, and it could be proton and alpha particle. So here we are also missing proton. And you can say we can also do electron. So all these particles also you can accelerate along with your atoms in the periodic table and can put in your solid, right? So depending upon what you choose, either you choose neutral particle, you choose charged particle, or third category will be, of course, your ions from here. Neutral, charged, and ions from the periodic table. These are the three categories with which you will be able to, create these kind of collisions into your solid. Okay. And one thing, it is very important, any periodic table or any ion that you choose, right, from the periodic table, so whether it is, so as aluminum can have different state, right? Aluminum can have 3+, aluminum can also have 4+. So depending upon the energy of the particle moving through a solid, it depends on its velocity. So which charged particle would it be? It will depend on the velocity. That means if it will change also its charge state. But charge state is generally not the topmost criteria that you use, because you are basically worried about the nucleus part here with the ion, right? So overall, what I'm trying to say through these slides is, just a second. Okay. What I'm trying to tell you is, we have a solid, we have the particle that is getting in, and this particle could be of three types, right? It can be neutral particles, it can be charged particles, and it can be your atoms or ions, right? So this one we know it's a neutron, right? This one we know it's your electrons, and this one we know it's a charged particle, atoms, which will coming from the periodic table, right? So these are the three things you can choose. Where you saw these happening in ion accelerator labs, right? You can go there. Then where else you can have this? There are other ways for your alpha, beta, gamma. There are other sources as well that can do it. But ion accelerator, you see, it is for the ions, but other sources will be for your alpha, beta, and gamma, else you radiate it. Third things, for neutrons, you have nuclear reactor, right? These are the three places where you can go and have this kind of interaction. Okay. Very good. So we understand what we are going through. Okay. There are some remarks. The remarks are, as I told you, energetic particle, it interact independently with nucleus and electrons. Guys, can anyone say what is the recoil? When this kind of interactions happens, what is the recoil? We can talk about the recoil thing. So energetic particle, it goes inside and interacts here with your nucleus and electrons separately. And for example, if this was your incoming particle, yellow in color, so this makes a collision. It replaces this atom because it tries to move this atom. And when it moves this atom, it creates a vacancy. So this red atom, it comes out of its position. This is a recoil. This term will be used again and again. So initial, this is the incoming ion or injected ion. When it goes inside, it is able to make a collision. I should use red color here, yellow, so that you understand. So this one you see, This is your incoming particle. It goes in this red solid. It goes and gets deposited, or even if it doesn't get deposited, it goes and go and make more collision. It made one collision, and in that collision, it is able to replace the solid atom from its initial position to here. And in the second case, it is it's just getting deposited here, right? This one. So yellow is your incoming ion, right? It goes, it is able to displace, this is the term I'll use, displace the first atom. And then on the second thing, this after displacing the first atom, it will keep on going and start making the collisions. Now, when it starts making the collisions, this is your second atom, right? And so on. Maybe it has the energy to, to displace this one. And if it, so this is known as secondary recoil. So these are the primary recoil, right? And this could be the secondary recoil, or it could also be that recoil itself now has energy and it is able to replace. So then all these secondary recoils that you will have, it will be coming after the second interaction, either with the recoil itself and either with the primary ion that you injected. So this term of recoil should be clear to you, in all possible things, because that is where this thing is. So I hope recoil is clear from this, right? Now, there is something we talk about is scattering cross section. This is also an important term into this. So recoil, scattering cross section. In the scattering cross section is the probability of interaction. So this is your solid atom. I'm using the same color. And then I have energetic particle that is coming in. What is the probability of interaction and how much it will scatter its way? Sometimes maybe it doesn't have energy to displace this. And even if it has the energy to displace it, how does this scattering happens? And this all is known by as scattering cross section, right? So this is very important. Now, these are some key points on it. So I will introduce you also with a book called the Book of Gary Voss. Anyone knows about this book, Gary Voss? Nuclear engineers should know about it. There is a book, Gary Voss, G. Voss. And this is interaction of radiation with solid. Generally, that is considered as the most updated book. It's come from a professor at the University of Michigan. And Gary Voss wrote that book. And after that, all these things happen. Sorry, this book contains all the details of all these things happening that I'm showing. So I make notes from that book. So I'm just taking key notes. It's a very intense book. Okay. So guys, now what is happening is your material. Okay. You have this kind of interaction happening. You had a solid here. And you have an incoming particle here. It goes in. It makes this kind of collisions, right? Depends on the scattering cross sections, right? It is able to displace it. Now, there is something which we know is, one is the scattering cross section is one term. That is very important. Second term that is important is the stopping power. What is the stopping power? Because this thing is able to, this solid is able to stop this energetic particle. So it is able to stop this energetic particle. See, you are not even able to see atoms today also with electron microscope. You need to have very high microscopy, and then also you see the signature of atoms. So you see the sizes are very, very small. So it's a very dense kind of a system here. It's not a, it's not something pen and paper model that I'm drawing. There will be an intense number of solid atoms here, right? All these are atoms. Now, when you're this thing coming, it is starting interacting from very beginning. And ultimately it will stop somewhere in your material, right? And when it stops, so let us do a 3D. Now it is getting in and it stops somewhere, you know. So, but you can calculate this thing called energy loss per unit length. And when you calculate this energy loss per unit length, right, that is your stopping power. And that will be your two things here. Energy loss are happening with neutron interactions and with electron interactions. So you have something called, you know, your nuclear stopping power and electron stopping power. And that is what you are going to calculate using STRIM, right? So I hope this thing is clear. We are talking about the scattering cross sections. That is a probability in which, you know, the atom will scatter. Then we are talking about your energy loss per unit length. And then what is the third one is electron stopping is dominant at high energies. This is also very important thing, that when the energy of the incoming ion becomes very high, so what happens is in the beginning you have this incoming ion, it can have energies from low to high. When it will have a low energy, in that case, you know, as the two billiards ball collide, it will be the same kind of model. So nucleus to nucleus will collide. But when it will have a higher energy, that means you have to imagine, you know, if like, you know, a rocket or something went through the sky, in that time it experiences a lot of a similar kind of force, like a friction into the atmosphere, or a kind of a friction into the actual solid. And that all comes from the interaction of this incoming with the electrons of this. So another takeaway from here is that electronic stopping is dominant at high energies, right? Makes sense, guys? I'm trying to be very in-depth because this is an important kind of, you know, concept, a very important concept I'm trying to introduce. Now, the fourth thing is also, if there is a very high energetic, so when the energy is very high and it tries to pass into the material, then what happens is these electrons of the materials, they get excited, right? Because, okay, it is stopping them, but it is also able to strip them. So this is already, and, you know, already a stripped ion is coming in. You know, it has some kind of state. If it is aluminium, it will have, you know, 3+, 2+, or whatnot. Then it is iron, it will also have 2+, 3+, whatnot. It is coming in. Now it is interacting with this. Not only this, it is able to strip the electrons of this while it interacts. So after interaction, this all becomes naked. So that's why you have kind of ion tracks, right? So this is the electron when they are high energetic. So what they do, it leads to the ionization of medium. So from wherever it passes, it will do this kind of, you know, ionization of the medium. So let me use a different color. So for example, if it is passing through, you know, this is the track of the incoming ion, right? So what will happen is, in between whatever atoms it meets, it will strip the electrons from there. Make sense? So this is the fourth point from here, right? Now, what is the fifth point? That all these atoms which are degraded, now they are, you know, all these electrons in the way, all these solid atoms, they have given some electrons. Now these electrons will be captured back inside. So this is known as ionization energy is degraded. Sorry, electrons are recaptured. And all these energy is degraded into heat, right? So we are not worried about insulator here, but in the insulator, electrons are captured in the defect site. So these are the main important points, and we will revise it again because this is very much important for us. Okay, let us quickly do a revision with another color here. So I'm talking to you about, how does the incoming ion interact with the solid. I introduced a term called scattering cross section to you, right? It is the probability of interaction. Then I introduced a term of energy loss per unit length or stopping power. And there are two types of this stopping power, nuclear and electronic. Third important concept I'm talking about is that electronic stopping power is dominant at high energies. So I gave you an example. If the rocket goes to the sky, it feels the friction. It's a similar kind of energy it experiences. And wherever the rocket goes, it leads to ionization of medium, or it leads to removing of electrons from that track, right? This is the fourth kind of thing. And fifth is all the electrons are recaptured. So this is the typical interaction we are talking about. When your ion goes into the solid, it makes nuclear stopping power, electronic stopping power. Both of this thing depends on your differential scattering cross sections. And whenever at high energies, your electronic stopping power is dominant. At lower energies, your ballistic, that is your nuclear stopping power is more important, right? And depending upon that, we calculate your final something called range. So this is where it is stopping is known as range. And that you will calculate using SRIM. Okay. Let us go to this one. Now, there are some other note. As I say, it's basically saying that nuclear is T dominant at low energies, nuclear interaction. So what does it involve? It involves bare nuclei at high energy, high particle energy, and nucleus and bound at low energies. So it's just simply, it is talking about that at high particle energy, nuclear interactions involve bare nuclei. And at low, it involves both nuclei and electrons. So guys, this is here your incoming particle going inside the solid, right? And the solid has electrons. So it says when the energy is low, it goes and tries to make an interaction because it is so slow. The time of interaction is so high that it tries to make, it with both, right? Now, main important thing here, nuclear interaction, it produces permanent atomic displacement. So you are trying to displace an atom from its position, right? Remember the Lee coil thing? You are trying to replace it. Let's again make them red. Inside atoms are red in color and incident ones are green. It is able to replace it. This to able to replace it, what kind of interaction is important? Nuclear interaction is important. Why? Because electrons won't be able to, it will be able to deionize it, will be able to do a lot of things, but it won't be able to displace it. The displacements will happen at the end, right? So that is known as your, displacements happens due to nuclear stopping power, right? And this displacement is very important because that is about radiation effects in solid. So these are the nuclear interactions they call permanent atomic displacements. This is one of the main takeaway. And from here, so overall, if I ask you to displace it, you won't be able to, right? With the electrons. And they say that, okay, these are the atomic displacement. Remember on the TEM, I showed you all these things. I showed you on the TEM, a lot of displacements, a lot of dislocations, and they say they are the reason behind the radiation damage and radiation effects. Make sense, guys? Okay. Okay. So this is the main thing. So only the main takeaway is nuclear interactions are causing the DPA. or they are able to displace the atoms. Rest, nothing. And this dPA is doing everything inside your radiation effects kind of subject if we talk about. Okay. Very good. Questions, guys? Am I too slow? Am I too fast? Any comments? Okay. This is what? On screen, what do you see here? You see electrons on the left, protons, you see heavy ions, right? Now, electron, does it have a nucleus? Can it do nuclear displacements? It doesn't have a nucleus, right? Proton, does it have a nucleus? No. Can it do some kind of the atomic displacement? No. Then you have heavy ions and you have neutrons. Can you see how much is the effect? So what is happening here is, I'm talking about something called displacement event. And now it should all make sense why I was introducing everything. This is your solid atoms. And now I am trying to bring in your energetic particle here. Now I told you it can either have a nuclear or an electronic interaction. Now here on screen you have electrons, you have protons. So if electron goes inside it, largely it is not able to do anything, right? It is a very lighter kind of a thing. And you see, this is the kind of event that it does, right? You see, the event is really a bad event because it is not able to displace anything. It doesn't have, you need to have a bigger kind of the system here to make an interaction and replace it. But electron, it's only a very light per particle. It does not have this nucleus which will go inside and do it. Similarly applies to proton. So due to their charges, they have a different kind of interaction. Proton also, you see, it doesn't. But any heavy ion will come, right? Heavy ion, that is something that I take from the periodic table from the bottom here, or something even, even iron, aluminum iron is considered. Let us take gold, heavy ion. It is heavy, it will go and start displacing everything. And then it will make a bigger blob like this, right? And look at neutrons. Neutrons are really, because they are charged particle, so the interaction is very different. And look at the kind of blob they are making, neutrons. It's a huge blob, right? What a big blob. So that means in this blob, there are a lot of displacements are happening. Lot of them. So this is like how it looks. So tomorrow I can give you a question. Does electron and proton will have large amount of dPA? And you will have an answer, no. And then there is a term called displacement efficiency. So displacement efficiency is that, here I sent an electron, and with whatever energy this little electron had, it is able to create a displacement event. Okay, but this guy, you see, neutron, with whatever energy it has, it could have created and destroyed the entire solid. But only efficiency is only 2% because there is a lot of recombination happening back. And that is, this is not a displacement efficiency. So electron, it's like a feather touch. It will go inside a solid. This feather touch is able to displace these atoms from its, if it is able to displace one or two, it won't be able to displace much. It will go and like a feather touch here, feather touch here. But this thing is like a machine gun, neutron. It goes inside it, it causes a bigger displacement cascades, and this displacement cascades, they get recoiled. they get recombined itself, right? So this is known as damage efficiency. So on your, this is a very important diagram, guys. And this is obtained, again, this is the book. Please note down this book. You have to go here. Gary was Fundamentals of Radiation of Material Science, 2007. This is the book that is in the market that I use and that everyone uses, especially at the PhD level, to understand these phenomena. Right? Make sense? Okay. I'll clear all things and move to the next slide. Okay. Guys, I'm trying to be very, how to say, no, I didn't have my video on, I didn't realize. And so guys, I am trying to take you from fundamentals, right? Now, what is the stopping power, you understand, right? I already gave you the idea. It is the energy lost by moving particle per unit length traveled, right? And how it is obtained? It is obtained by product of energy transfer to a recoil, okay? Because, your particle is going, it is making an interaction here. It is able to displace them, and then it becomes a recoil. I'm always trying to use different colors here. Red color for the solid atoms. It is able to, this is a recoil, right? So we are saying, what is the stopping power? How much this yellow atom or the incident atom is losing inside this material? And they say it depends. It is a product of energy transfer to recoil. Okay, how much energy? So in the beginning, if it has, say 1 MeV energy, how much energy transferred here? Because the energy here, it will be decreased by that amount, right? So how much energy it is able to transfer, and the differential scattering cross section over all possible values of T. Now, this is very important. 1 MeV, when it starts making an interaction, it is a very energetic particle. It has maybe a different probability of interaction, it interacts, say, more. Now, when the energy after giving to this guy, it gives, something called X MeV, or you can say something like, 0.1 MeV here to this guy, recoil guy. Now, its energy is reduced from 1 to, it will reduce from 1 to 0.99 MeV. Now, at 0.99 MeV, it will have a different interaction probability. Then it will give this kind of energy to this guy. And then further, it reduces the energy to 0.98 MeV. Like this, it will keep on reducing energy, right? And your differential cross-section will change. So this is your differential energy cross-section that you have to integrate over all possible over all possible energies of recoil to obtain the average energy, right? So if you do it, this is here. This is the energy. So energy of the recoil is, please remember this. This is even some questions that I would be giving you. Also could be the part of the exam. T is your recoil, right? And this is your differential cross-section, which depends on the energy of the recoil. And this is your length on which it is being able to transfer the energy. So here we have, actually, you can see here we have three main things, right? What are the three main things here? This is the energy of the recoil on which this stopping power depends. And let us do this dE by dx here, because this is dE by dx, right? And then the second thing it depends on, let me change the color for you. This thing is the second color, right? So it depends on here, two things. As I told while I was, doing your thing on top. So it depends on your energy cross section, and this energy cross section will vary over all possible values of recoil. How much energy it gives to the recoil, your cross section would change as it will slow down and it will create more recoils. Your differential energy scattering cross section will change. So this is one thing, and it depends on the second thing that we know is your energy transfer to recoil, right? These are the two things. And here, that is what we have done. So stopping power, they defined it as like this, where n is your, total number of particles. Okay, that is fine. And this is your final thing. This is your recoil energy, and this is the energy cross section. Right? Now, guys, on your screen, what you see is, you see a copper ion, right? It goes into some kind of solid. In the beginning, copper ion goes, because it has energy, it won't stop. It goes inside. So this is a number of ions, or you can say it is very much looks like a number of ions here, but it is more of, here is a neutron stopping power. So it goes inside, it loses less energy. But after a certain point where it is going to stop into the matter, and if I am able to plot the range here, I can plot the range like this. This will be the range. So there are three things on screen for you right now. And guys, this is right now, we are on very fundamental thing. We should really pay attention here and, try to understand the concept, because this will make you solid. So this is what is happening here on screen is, you have neutron energy loss, you have electron energy loss, and what is happening? You have a copper ion that is going in the solid. How these curves look like. Now, what I'm trying to say you is, on top, this is not showing you a curve which is known as your range curve, which will look like, almost look like this, or maybe more, it will look like this. This is your range. Yeah, this will be your range, right? Now, why it is like this on screen now? This is your electronic nuclear, and this is your range. Now, incident particle came, copper ion came inside. In the beginning, it did not, you see, this is range is where it stopped finally. So before stopping, it was doing all kind of interactions, right? So it was doing interactions. It is not possible that in the beginning there was no interaction. And if you take a takeaway from the last class, from the last slide, I said electron at a very high energy, electron energy loss is dominant, right? So at high energy, electron energy loss is dominant. Now, when it is just entering the solid, energy is very high, right? Therefore, it has this tendency, it has a maximum electron energy loss in the beginning, because it has very high energy in the beginning when it enters the solid, right? Remember that thing I talked about, that it does like a zoom, and it with the electronic energy loss, and this all happen at a very high energy. So in the beginning, it has a very high energy, it enters the solid, and then this electronic energy loss, it starts to degrade, right? But in the beginning, because it has a very high energy, so to have a nuclear interaction, it needs to have a certain time that it should give to have those kind of interactions happening, right? And to do that, in the beginning, we have very, very less energy. So it makes it in the beginning there is, no energy loss, but when it goes, it deposits here, and then, maximum deposition is happening here. No interaction in the beginning. Now, let's repeat this. What I'm trying to tell you here is, and this is like the Bible or the fundamental. In the beginning, when it enters into the solid, dominant force is electronic energy loss. Now, electronic energy loss, that is a friction, it has slowed it down that much that finally it will stop in the material somewhere. And when it stops, then it loses maximum of its energy by neutron interaction. And that is where your dPA is happening. That is where your displacements are happening at this point. And that is why if you plot a range, the range that I plotted, it is around here at this point. So when your atom, it enters the material, electronic energy loss will happen. Now, gradually, it will lose enough energy that it goes inside the material and it does this nuclear interaction, right? To have this nuclear interaction, energy should be slow. Who slows it? Electronic energy loss slows it. How do you write electronic energy loss? dE dx by E. On which things it depends on? It depends on the energy of the recoil that is happening and the scattering cross section that is happening. Make sense? This is clear. This should be clear by heart. Okay. Any questions, guys? I'm looking for some interaction. Is it going good? Hello, you guys are here?
Yeah, I'm understanding.
Okay. So this is where the thing is. Now, from this stopping power, we have the concept of range, right? Now, with this range here, now this is the measure of path length. So finally, how much distance it has covered into the range, how much distance your initial atom it covered before stopping is known as range. It is a measure of the path length in the solid traversed by the particle, right? That is the range. And if you do here, range is integration of dx, because what we were doing is we were trying to calculate the energy loss in the small distances. How much energy loss it is losing, into it. Or if I do in a 3D, this was my solid, how much energy loss it is doing per dx. So range is the integration of the entire length on which it is losing energy. So that is why there's an integration of dx over r, right? And they say also equivalent to mean free path, approximately equivalent to mean free path. Mean free path is how much it will go, mean free path is another term that doesn't come directly from radiation effects, but it comes from, other part of the physics where they are studying a lot of, collisions in liquids and everything, and they call it mean free path, or, in lesser dense material. So this is how we calculate here is something called range, right? Olamide, you have some doubts today? Where are you in the class? Olamide, are you here?
Yes.
Okay, you have some doubts? Is it all clear? Or do you have some doubts? Is it easy for you or is it tough for you guys? because in the future you will only see, these curves, and this should not become very complicated for you. That is where, you start seeing them again and again. In the beginning, you have electron energy loss. Then when your atom stops in the matter, it does maximum interaction by neutrons. Nari, this is easy for you or it's tough?
Yeah, I'm following just fine.
Okay. So this is clear. Okay. Very good. Okay, very good. Now it's becoming a little bit complicated, guys, because this will only be able to make you solid in the field, and there is a little bit of physics involved in 1 or 2 chapters before we get into those microscopy image and everything, and we can do also AI project. But before that, we have to go through this understanding because that is how the subject is built. Okay. Now, here we are doing something even a little bit more into it. So we are now talking about, we're going one step further down. If you see, the topic is that electronic stopping power are determined by effective charge of the incident ion. And if you notice that I've been talking about it, that the charge changes as the incident ion velocity changes, right? So incident ion velocity, when it changes, so what I'm trying to say, this is the incident ion. If it is very high, 1 MeV, versus it is something like, say, 0.5 MeV. And let us say the ion, the incident ion is iron. It will have different electronic stopping power. So one leads to the other. So this is here the energetic particle getting into very high energy. It will have a different charge state. This will have a different charge state, and they are all going inside the solid. Right? So it is like this. And so point is, with energy, charge state changes. And with charge state, your electronic power changes. So they gave this kind of thing here. So if you see here, and this is a little bit important. So in the beginning, this is the electronic stopping power cross sections. So we have 3 kind of things. One is E by 1 by half, and other is 1 by E. And we have the proton energy that is going from 10 raised to the power 3 to 10 raised to the power 8. As the proton kinetic energy is increasing, you will see here energy is increasing. So if energy would increase, what will happen? You will have more electronic stopping power. So you will see here, your energy is increasing here in the EV, and this is proton. So you are going like this, E 1 by half. So E square root of E, right? And here it is 1 by E. And this is how your electronic stopping cross section is changing as your proton kinetic energy is increasing. Now at a certain point, more is the energy. So this is divided into two regime. So 1 by E would mean more is your, or you can say less is your kinetic energy, more is your electronic stopping power, right? And that is what you saw. and then it decreases. So overall, from this slide, the main thing that you can just remember is, because it can get a little confusing for you, that you have these two kind of interactions, Coulombic and E 1 by half. So this is 1 by E, and then this is square root of E. And this is your cross section, how it changes, you know, for when it goes from proton energy is going from here to here. So this is, because this is proton, so it has a slightly different thing, and definitely it is charge dependent. I will get back to here in a bit, because this is an important part, but this will be more clear to you from the next slides. Okay. So what it is trying to tell you is the same thing. There are three, when we talk about the stopping power, especially electronic stopping power, and you see here, guys, on the screen here, this is important, that your electronic stopping power, it becomes active at a higher energy. So for your high energy would mean, so when you do, you know, have you heard about Large Hadron Collider, LHC, CERN, where they have, you know, a big accelerator, LINAC, where they're accelerating particles, and they have the energy of 1 GeV. We talk about that kind of range to see a very, very strong electronic energy loss component. The kind of things we are doing by SRIM. By SRIM, what we are doing is we are trying to this was the incident particle. We are trying to make this kind of collisions with the thing here, solid here. And it is doing, we are not at all in this energy range. We are in the energy range where your nuclear collisions are more dominant. So despite it is active, so that is why what we see is that in the beginning, where your nuclear stopping power is active, and this is the electronic stopping power range over a very, very big range, very, very big range, right? So this is here where in the previous slide, when you have your, it was the inverse plot. Now it was here. Okay, we see it. This is on the previous slide. This was here, E1 by half, right? So here, E1 by half, and then it becomes 1 by E, right? So it's thing that I am plotting over very, very big ion velocity. And you see it inverted in a, not inverted exactly the term, but if I plot a nuclear energy loss, I'll plot it there. Now, we are in a range, and I'm showing you the entire plot. If I have an energy of 1 GeV, this is how it will behave. Now, there are three things written on top: low energies, intermediate energies, high energy, right? Let me change the color. It's not letting me change anyways. No. Okay. So this is here low energy, intermediate energy, and high energy. So it says for higher energy, we follow something called Bethe block. Do you know this Bethe block thing? This comes from, you know, Bethe block. Bethe block is something which is 1 by E. This is the kind of thing that you see in your thing. 1 by E. When you see that when you come, ion velocity comes, it interactions, it starts happening like this. So it has to reach a certain energy to make this kind of thing. My point is, if you go back to the previous slides where we were dealing with your, where I introduced you this thing, we are already at that kind of energy. Remember, I said that electronic energy loss, when it starts, because your energy is very high. So because your energy is very high, we are at already this kind of thing where we are degrading like this. Because it is that time, especially in your velocity range that you have for the ion, that is that time that it becomes active, right? So here, when I see this, I am already, with respect to the curve that I showed you, I am already at this region. And I am not showing you the story behind what is happening, right? The story before that, when it was slow, we were not in this region. And when it was slow, that's why the inverse happens, because in the beginning, you start like this. You have a high energy into your material, right? And then it slows. Then intermediate energy is here. Then it is following this kind of curve. And then a low energy is here. When I'm trying to introduce something inverse to you in the beginning, but then I hesitated that I don't know if you have understood. So this is how things are. So this is the material. And in the material, in the beginning, you will follow this curve. This one. So this is where you saw. And then what happens is, you are at a region, intermediate region, because it in the materials 1 MeV ion, when it comes in, it is 1 MeV, right? Now this is your third region here. Now in the second region, it follow intermediate energy. In the second region, it is following the intermediate energy. Why? Because it has slowed down, right? So this intermediate energy, it will follow here. Somewhere. And further down, here, it will follow a low energy. That is why they are also putting your nuclear stopping power at this region, because the energy is slow. And now, so this is here is also nuclear energy where it will start depositing. So this is the kind of curve that we have. So this is what I was trying to tell you from the previous slide as well, that high energy, this becomes that what we see in the beginning of our material is this, right? Which is a Bethe block formula, right? So this is like kind of your master curve, that this is, main takeaway is 1 by E here, right? And square root here. This is how the dependence is. Square root E is here. 1 by E is here. And when you start your simulation, you see this more, then you get confused. But you should not get confused, because here in the beginning, your electron energy is very, very high. So it will follow the high energy region. You can say this is a high energy region, so it will follow this kind of a curve, right? As it progresses into the material, then it becomes intermediate. So it will follow intermediate energy kind of a tendency. Now, when it becomes further down, further slow, and why it is becoming slow? Because when it travels, it loses energy by recoil. It keeps on giving energy by recoil. And then it further stops, and it is here. Makes sense, guys? I hope it is all clear to you. Okay. right? Good. If you have understood this, you understood today's lecture actually. Now we are seeing them again and again. I saw that, there will be a lot of examples because this is a high level class, and for the high level class, we take a lot of examples from the papers itself. Now, what we see is the stopping power, and I can ask you to calculate the stopping power, and you should be able to calculate the stopping power by, going on that formula where you had its stopping power was dE by dx, and it was proportional to energy of the recoil, and it was also proportional to your cross section that was changing with time, right? That was changing with energy of recoil. These were the two things, differential cross section. And if you see, the unit is dE by dx, right? keV per micrometer. Now, on your screen right now, you have a plot where you are losing energy in micrometer. You have to start thinking, guys, in terms of micrometer now, not in meter, because all the range curve that you will be plotting it in micrometer to have a full visual. You will see a lot of ion will stop after 6 micrometer, 7 micrometer. So this is a very common unit. So you should start working the micrometer kind of thing in your brain. So now on your screen, you have three things: electron stopping power, neutron stopping power, and then you have stopping power of protons, right? Now, they say electron stripping from bombarding ion above a threshold velocity. Now here, you should be here when we talk about our Bethe block thing in the beginning. And then if you see here, this is again an invert because this is ME by U. And here it is losing its nuclear stopping power in the beginning, where it is following that kind of tendency, right? You have to, it's the same thing. You can correlate, you will be. It's not a big deal. Okay. Guys, this is what you are going to compare. You are going to compare this thing by SRIM. That's what I'm looking from you. This is the calculation based on SRIM, right? So what is happening here is, so as I told you, nobody will show you the story. So this is the story. This is the story where, it has started becoming very high. So what is happening is, if you see here, we are going in the opposite direction. Why? Because these are some kind of plots that helps you to decide which ion energy you should pick. But this is not what is happening inside the material. Inside the materials, in fact, inverse is happening, because inside the material, you are going from high energy to low energy. You're going from high energy to low energy inside the material. That's why your electronic stopping power was like this. But this one is a plot of ion energy. That at this ion energy, this is my stopping power. So inside the material, you are literally going like this. That's why this kind of confusion is happening. This is inverse, but you have to go and look at the scale. If the scale is the distance here, distance inside the material, then you will be correct in putting, you will be correct in putting it like this. This is a distance inside the material. But right now, in the distance inside the material, you will also have going from high energy to low energy, right? I'm just talking about the electronic stopping power, just to make understanding easy for you, from high energy to low energy, right? That's why when you look here, you get confused why it is doing like this. When I introduced you in the beginning, I introduced you that this is how electronic energy is varying. Yes, this is how exactly it is varying. We are going from high energy to low energy. And when you go at high energy, you have a bigger, you see here a bigger magnitude. When you go at low energy, you have a smaller magnitude. And that is where, you know, you have that thing where you have a square root kind of thing. So this is to be important, and this is what you're computing using so when you will run a SRIM calculation, I don't have it on my Mac, but I'm happy to give you a tutorial. I'm also there, on campus another 2 weeks. Starting coming Saturday, I will be there. So I'm there, and if you do not understand SRIM, you can come. But when you run a SRIM calculation, and if you check box for electronic stopping power and nuclear stopping power, you will be able to get this kind of curve. And I am looking for this kind of curves from you. So you should be able to understand them as well. Right? Okay, this is very good. Now, okay, guys, now we are something coming across electronic versus nuclear stopping power. Okay. What is happening now? We have come from, we will say, this region here, dE by dx, which was going, and this is inside, I'm inside the material. So my range is distance here. Whenever my range is distance, I'm inside the material. So this is some kind of a plot. And, you are going from here to here. And this is your dE by dx. Right? Now, what is here? Also, your nuclear energy becomes very dominant. Now, what is this nuclear energy now? We'll talk about that. Now, because of this nuclear energy, your DPA is happening. That is, your displacements are happening, right? So what is the displacement energy of a material? Can anyone tell me? What is the displacement energy? This is a term that we know from, high school science.
It's the energy it takes to displace an atom from its
Very good.
position in the matrix.
Very good, very good. So there was a convenient approximation, you can say, that Kinchin-Pease did. And Kinchin-Pease is also the term. And guys, you have to go and download the SRIM this week. And next week, I can run the code. I think if somebody brings, I don't have it on Mac, and I have gone with a lot of AI stuff, so I don't want to disturb that. But if anyone has Windows, they can have SRIM on it. Or maybe I bring my another laptop. And there is a term that you will find again and again is Kinchin-Pease. So anyone will ask you, did you find your displacement using Kinchin-Pease? What does that mean? So Kinchin-Pease, basically, it gives you a very convenient approximation. So this is like a pen and paper model. What it said is, in the beginning, you have your incident ion. They go and they make an interaction with atoms of material. Now, so here is the primary knock-on atom energy. It says, if I need 25 EV, which is a very small energy, actually. If I need 25 EV of energy to displace this atom so that it becomes, a knock-on and it leaves a vacancy here. If I need 25 EV, then because it loses a lot of its energy in the beginning, I at least need to have 50 EV of the energy to make one displacement. Make sense? So he says from ED to 2ED, there would only be one displacement. Because in the beginning, 2ED would mean, so what I'm trying to say here is, I'm just trying to give you a very convenient or a pen and paper model that how much energy do you need to displace an atom from the main solid, right? What does that mean? How much energy do I need? So you are giving an experiment here. I'm telling Olamide, go and deposit iron into my iron. And you will say how many iron atoms will be displaced. So I will go here, I will say go and put it. And then now I'm using reverse color. Forgive me for that. So this is here a yellow solid right now. So you will say, please tell me how much energy would I need to displace one atom? And I will say 25 EV of the energy you would need. So this is, guys, our yellow color is a recoil. It will take 25 MeV energy. So the idea was at least you need to give me 50 MeV energy. Because 50 MeV energy to create one displacement. Why? Because 25 MeV till the time it reaches here, it should remain 25. So it takes an kind of a upper limit that in the beginning it comes with 50 EV, and in the 50 MeV, what will happen is it will try to, you can call it EV, guys, not MEV. It's a very big MEV. So it has a 50 EV energy. In the beginning, it comes. Now, it is able, by the time it interacts here, it will, become 50 minus X due to electronic energy less, some kind of thing. So it will have finally 25 MeV minimum, and still it will have some energy left. So that's why they make it a very simple and convenient approximation that your energy should be at least from ED to 2ED, it will only do one number of displaced atoms. And after that, when, right now, we are in the energy range of 25, that I'm calling it a displaced energy. We are giving it 50. After that, when we give 100 and when we give 200, life becomes very easy for us, because then your number of displaced atoms, it keeps on increasing proportionally. In the beginning, it will only make one displacement, and then it keeps on increasing proportionally. How much energy you will put, it will keep on going up till a cutoff. There's a cutoff. So it makes a very, very simple model. As you give it to some, beginner, and you ask him that, do this. And this is your Kinchen piece model. Right, guys, I'll take 5 minutes break because my throat is kind of hurting, and I'll be returning in 5 minutes, and I'll touch again the base. I'll see you in 5 minutes. Hey guys, oh, my video is again closed. Okay. So on this note, I just have an idea. So Nari and we have Rishi with us, right? Because Olamide is new to the stream. So guys, not in the next class, but the class after the next week, right? Can you guys do a small demo of the stream? So your homework, which is, I thought earlier 3 weeks because nobody knows it, but most of the people have done stream before. So Nari and Rishvik, I'm excluding Olamide just for now. Can you do a small presentation and tutorial in 2 weeks, and that would be your homework presentation? And then I can also ask Olamide to give me a personal presentation following that, because he hasn't worked with it that much. So that means I can tell you the date that is on my mind, calendar, on 18th of February. Nari and Rishvik, can you give a combined presentation on just telling us how to use stream, and first of all, and then discussing the various plots? I can give you the question and answer, the homework that I made after this class, and you think you both can do it, and that will be your homework.
I'm just a little confused. So are we gonna actually complete the homework that you like assigned or like drafted, I guess?
I mean,
to
the
make the
homework that I
presentation?
assign is very simple. Let me show you the homework so you guys are not confused, but I think that is the best way to learn, is to interact. Otherwise, it looks like I keep on giving the knowledge. Hold on, let me show you the homework. Very quickly, you can see my screen. Okay. So guys, your homework is very easy, because I'm not trying to give you, I should make it 2018th, because earlier I thought that you guys have no familiarity. So let us do it in 2 weeks. And yeah, and you both guys can team up. So what is the homework? So you can say, simulate 10 kV argon silicon. So calculate ion penetration depth, number of vacancies. So this is your question 1. Then the second thing is compare. So first was just to run a trim calculation. Then you have to compare the damage analysis. So you have to run it here, 50 MeV iron in gold and silicon, and you have to calculate this. So one of you can do question number 2, and one of you can do question number 3. That is it. So I can right now even can assign you. This is the one that is, just for learning purposes. And to here, and you can, do this question. I can say Rishi can do this one, and it is an online doc. And this question, where I say little bit advanced, but it's not very advanced. And I think Nari can do it, and you can ask me the questions. And then I will also add a question here for you, Olamide. And you have to discuss this thing in class and run the simulation. It's a very small homework, it's not at all tough. Your 2, 3, and I can add something also for one simulation. I can add it for. Okay, this one you can do, Olamide, because you have told me that your background is little. So this one you can do, learning purpose, Olamide. And you have this in your documents. And if you get a hang of it, it's fine. If you don't get a hang of it, I'm open to discuss. But let Rishi and Nari give the presentation. And then so you have to show me the entire working. These curves, they should not take you more than 1 hour to run. And you can give a tutorial on how it works. And then Rishi can show this part. And Nari can show this part. And Olamide, if you can show this part, if you don't, then you show us this part to me in a personal presentation. It is fine, because I don't want to create that kind of a pressure. But this will be dictating your homework. And I share everything in the Google Drive. Yeah, I just removed the additional notes. So what are the students should submit? They should simulation setup screenshots, plots of ion range and damage profile, comparative table, and short discussion on the observed trends. Yeah, so this is good. I was giving it to one student, but I think you guys made it easy. Your name is here, and this is being shared in the same drive, and this drive is shared with you. So I do it now. I try to be on Canvas, but with this one, anyone with the link, I will send you the link. Or right now also I can give you the link. You all are viewers. I've also given the link on the chat, but if you lose it, you have the link on the chat. And you should be able to access this document. And once I can also start putting them on Canvas. I should have someone working with me this week to set up my Canvas. Okay, I have Olamide who says okay. And this is what you're doing. Cool. Okay, you have the homework, 18 Feb. This is, I think, a good idea to keep everyone in charge. Okay. We have little time left now, but it should be productive. Okay. So guys, this is here. Okay. Let us quickly discuss this. We are trying to calculate the number of displaced atoms. And if you don't know this huge, electronic stopping power, nuclear stopping power, and all this knowledge, if you don't know, then the simple pen and paper model is, I give you a material and I ask you to calculate how many atoms will you able to displace in here. You asked me one simple question. What the question will be? The question will be, this is the incident ion. And you will ask me, please tell me how much energy does it require to displace this atom, right? And I tell you the energy is 25 eV. To displace this atom from its position to here and to make it a recoil, I need 25 eV, which is very small, but okay. I need 25 eV. And then you will say, okay, but there will be a lot of energy lost as soon as this incident ion enters the solid. There will be a lot of energy that will be lost. So to be safe, you have to give at least 50 eV energy. And if you give 50 eV energy, I'm sure one displacement would happen, right? But imagine if I give it not 50 EV, but I give it only 25 EV, then what will happen? 25 EV is the energy required to displace, and I only give it 25 EV. No displacement will happen because by the time it reaches the atom, it is already below 25 EV. So a safe number somebody told. So this is a very convenient approximation, or you can say it is a very approximate approximation where you are trying to calculate the number of displaced atom based on the incident energy or primary knock-on atom energy. And this is your primary knock-on atom, but I'm talking to you about here. I'm just trying to make it very easy, but it will follow the same trend. So primary knock-on will be this recoil now. It will start making all these collisions, right? So what is the minimum energy that we need? We need much above the threshold energy of displacement. Threshold energy is 25 EV. I need much more in the beginning to start with. And there is only one displacement happening between 25 EV and 50 EV. That means between threshold energy of displacement and 2 ED. And then everything becomes linear. This is your Kinchin-Peace model. Let me know if something is not clear. And very commonly known as Kinchin-Peace. You will go in your swim thing. There will be two things that will happening, Kinchin-Peace and full cascade. And that is why there has been there's very big paper of, if you Google my scholar profile, I have one of my most cited paper that is on SRIM. And there I compared Kinchin-Peace and full cascade, both of them thoroughly. Right? Now here, this is your, now, when you go on the SRIM, you have two options. Okay. Now, this is the similar thing. We have talked about it a lot. For the electronic energy losses, it's the same thing. Here again, we have to go in this direction inside the material. Please check if it is energy or there should be distance at the bottom. If there's a distance at the bottom, then it will start following this kind of a curve. But if there is an energy, then you have to have this kind of curve, which is inverse. At higher energy, it will be this. And it is the same thing coming again and again because this has a lot of papers information. Okay. Same thing, guys. Now, this is here. Let's go to the next slide. Okay. Now, there are two things. One is Kinchin-Peace, and then there is something called modified Kinchin-Peace. So guys, this is an important term. And I can ask you this thing. Kinchin-Peace, I told you. Then after Kinchin and Peace, there come three scientists. Norget, Robert, I think Robinson and Torrance. This is common NRT model. So they made the model more sophisticated. So from Kinchin-Peace, you go to the next model, and this thing should be very much clear. The NRT model and the Kinchin-Peace model. These are the models for atomic displacements. So here, it changed this thing. Now, if you go, it introduced something called 0.8. So this was your initial thing, 2 ED, right? Where you will see that 2 ED was there in the curve. Remember 2 ED, only one displacement happens. Now they also introduced something called 0.8, and the formula should be somewhere in the next slides. They introduced some term of efficiency in the denominator at 0.8. They modified it They thought that it will smooth it more. And then that becomes an NRT model. So from Kinchin piece to NRT. And I will touch the base again on this. Okay. The main idea is behind that introducing you NRT. This is mostly coming from there. Yes, here. Now, what is NRT thing? NRT model. It removed the simplifying Kinchin piece assumption of no defect production at high equal energy and accounted for some in cascade recombination. So what is happening, guys? The one that we just did was a Kinchin piece, where with Kinchin piece, you had this kind of thing in the beginning from here to here, 2 ED, there is only one collision. And then I told you everything start becoming a linear thing. That means what is happening here is, if I give you 200 MeV of energy of ion and your displacement energy is 25 EV, then your number of, this is your displacement energy, right? TD. And this is your incident energy. Now, your number of collisions that will happen is 200 MeV by 2 ED, right? Makes sense? 2 into 50. This will be your number of collisions. It's a very, again, very general thing. So that is why it is 2 TED. That means why they are putting 2, they are just making it safe. You will say, don't, let's not do it. You will say, if one atom has threshold of 25 EV to do a first displacement and total energy is 200, why don't you divide? Let's call it 20, right? So for one atom to displace, I need 20 EV and I give you 200 MeV. And I ask you to calculate total number of atoms. What will you do? 200 MeV, you will convert into 10 raised to power 6 EV and you give me 20. And you will say, Shraddha, it will be 10 raised to power 7 atom displaced. So easy. Makes sense to everyone, right? For one atom, I need 20. Then if I 20 EV and if I give you 200 MeV, right? How many atoms do I displace? Let's make it more simple. Let's make it more simple for you, so that you understand what is happening. Let's make it EV. EV. And I give you 200 EV energy. So for displacing one atom, I need 20 EV. And I give you 200 EV of energetic ion coming into your sample. So you will say, just, do it 200 by 20. So answer is, we'll displace 10 atoms. Now I tell you, but we'll also have losses. Okay, you say, let's make it more simple. If you consider the losses, let's have a 2 here to be safer side. Then we'll have at least 5 collisions of 5 displacement atoms we will have, right? So in the beginning, this is happening. This is one, that's what we discussed in the last slide. And after that, if you keep on increasing it, it becomes like this with the Kinchin piece model. And after that, energy is very, very high. You are somewhere here. Then Kinchin piece model, it did a very brute approximation. It made a straight line. It says nothing is happening after that Just everything is straight. Because he says, once you will have all these atoms that have displaced, now recombination will start taking place. And so it just made a straight line. It just says, it will, till there will be EC energy and it will stop. Now what NRT did, it refined it. So for NRT model, what it did, it says, no, it doesn't stop, but instead we should, make it a little bit more fluid or a little bit more, the model should be a little bit more in consistency with the reality. Let us include this factor of 0.8. And what does this 0.8 will do? This 0.8 will account for the recombination, right? Then it's not a straight line. So overall, we are going from Kinchin piece to NRT. Kinchin piece was following this kind of approximation. NRT is following the one that I'm drawing in the green. Sorry, the color is not changed yet. This is the one that NRT is following. And you should be knowing about this Kinchin piece and NRT by heart. And this could be one of your homework questions when the second homework comes. What is the difference between NRT and Kinchin piece model? Both of them are used for displacement, just that one introduced this special 0.8 factor to account for some kind of in-cascade recombination. And the current international model is based on NRT damage model. It is not Kinchin piece. It's a modified Kinchin piece model. And this is what we are following right now. And this is what is in the stream too. Okay, guys, with this, I think we can end today's class because then it is becoming a little bit more complicated and I'll get there. It will take another 10 minutes to explain the next slide. So we are here and these are the fundamentals of the class. I hope it becomes easier and easier as you go, and all these concepts should be thoroughly ingrained in your brain. That's the idea. And once I think you are able to do this, you should be able to understand about all these electronic, nuclear, and you should be able to compute them really nicely. I'll try to post this recording online and then see you then. Okay, bye-bye.